Okay, so you can see my screen.
Yes, sir.
Okay, so everyone start writing P in the chat window. And we resume this. This was the box which we ended up yesterday. So we learned a computationally inexpensive method of computing the variance of a random variable. Yeah. So rather than computing it from the squared deviations from the mean, so you should always try to speak it properly. So whenever you see x minus mu, because this is the mean and x is the random variable, so you should think of it as a deviation. Deviation itself is a random variable. So this will be then squared deviation, and this will then be the expected squared deviation. That is what we mean by the variance. Now, conceptually, this one is better because this conveys the idea of variance, but computationally, this one is better. Yeah, never think of this as the definition. This is the definition, and this is the computation. And yeah, we also proved it. I mean, the proof is much easier if you use the fact that E is a linear operator, right? So linearity allows this to be proved quickly. And the good thing about that proof using linearity is that it works. The same proof applies to both discrete and continuous. So for example, this proof given by the author only works with discrete. You have to repeat it for continuous, but that proof based on linearity is applicable to both. So yeah, and if you want practice, then these two examples, one is for discrete and one is for continuous. That's just obvious. So the next thing which we want to, yeah, one point must be made before we move on to the next topic. It's better if we go back to that diagram. Yeah, this diagram. So this diagram was the motivation for introducing variance, and of course, then you can also say standard deviation. So variance will be sigma squared, and yeah, standard deviation will be sigma. So the reason we needed this is to be able to compare two distributions. So here we can say that, okay, this has a smaller variance and this has a larger variance. So we compare the variance of the two distributions. When they have the same mean, the variance tells us, okay, there is more uncertainty in this one than in this one. Now, this method of comparing two distributions, two distributions by by their variances, right? Or by their standard deviations. This works only when these numbers, because I told you whenever we bring something, some problem into math, we get rid of the units, right? So this x, although we write 1, 2, 3 here, 1, 2, 3 here, but they will represent something in the physical world. So it is misleading if they come from different physical quantities. So let's say this x came from mass and this came from height, right? Or even if they are both actually, if this also is mass and this also is mass, but this is mass in kilograms and this is mass in grams. Now you can't compare these two, yeah, because the numbers don't tell you what method was used to go from the physical units to the mathematical numbers. So that is why this method only works when the two random variables have the same units. Okay. I mean, they had the same units and then you got rid of the units in the same way. So you should actually read this very carefully, this part. I told you the crux of it, but if you read this part, this tells you that you cannot rely on this. And later on in section 4.4, we'll learn a way of dealing with this problem. Yeah, we'll have to do something. So the upshot is that uh, when we start with the variance or with the standard deviation, we have to modify it in some way so that we can compare things from different units. Okay. Um, Before that, let's get to another problem, and that is, mm, let's start a new blank page. Okay. So when we write expectation, okay, expectation, and I say expectation of x. So we either write e of x, yeah, whether you write the bracket or not is irrelevant. So because even if you write ex, it's still acceptable because there is no way e can be interpreted as a random variable itself. So yeah, the bracket is optional. Um, and another way of writing this is mu, and it's better to write it with an x. Now this allowed us, I'm now writing it, to write the expectation of another thing, which is another random variable related to x, um, through a function g, right? So expectation of g of x using this notation is very straightforward. What do? We write e g of x, right? And here we just write mu, and the subscript, we replace the subscript with g of x. So this was very easy, right, to handle. Now we want the same method to think of the variance, because we know it, but actually it can come from here, right? So if g of x is x minus mu, no, I don't need to repeat that. We already know that. So there's no point in repeating that whole thing. So I'll start, instead of expectation, let's start with variance of x. We also know variance is also an expectation, but we just want to remind ourselves. So one way of writing this will be VAR of x, right? As I said earlier. Another way of writing that will be to write sigma squared for VAR, and then you write x in the subscript. And both of these, by definition, are simply um, the expected squared deviation, or the mean squared deviation. So this is the mean, this is the squared, and this is the deviation. Expected squared deviation. That's how you should read it. That's what we mean by the variance of x. Now, using similar methodology, we would like to think about the variance of some other variable which is related to x but not x itself, and it is g of x. Just like we did it for expectation. So how should we write the expectation, or how should we define the expectation? Not the expectation, sorry, the variance of g of x. So how will you write it about? Can someone suggest? So if I start with variance, what should I do? Variance of, what should I write instead of x? Hmm? Tell me.
G of x.
Yeah, this will be g of x. And what should I do here? Sigma squared
G of x.
g of x. You see, that's the advantage of using this subscript. And what will happen there in the definition? expected value of, I know I will have a square, right? So I'll start with that. I know I'll have to subtract the mean. So the mean of what?
G of x.
Yeah, so I'll have to write mu g of x, right? You see that thing, that thing will help us. And this will be, instead of x, this x will now be replaced with
G of
g
x.
of x. Yeah, so you can construct most of these definitions yourself. Once you have that, the rest is a piece of cake. You just write those two formulas. Yeah, for discrete you will have a summation of something, and I believe you can write that easily. And for continuous, it would be an integral, right? So let's summarize what I just explained to you in a cleaner way, because the textbook has a very clean presentation. Yeah, so now this is the summary of what I just said. If x is a random variable and the probability distribution is given to you, f, that f will be either a PMF or a PDF depending on whether x is discrete or continuous. And then we can think of the variance of another random variable. Let's call it g of x. And yesterday I also told you that although we write g of x, but what we mean is g composed with x, because x itself is not a number, it is a function. So you always need to imagine that x, if you start with a sample point s, so first you have to apply x, the random variable, then you will get a number, a real number, and then you have to apply g on top of that. So if you think of it as a single function, it would be g composition x of s. Yeah, but right, somehow probabilistic guys, they don't like this notation, so they write g of x. But we know what we mean by it, okay? So you should not get confused by that. Okay. So yeah, and so you see this sigma squared subscripts g of x, sigma squared subscript g of x. Yeah, and what he didn't write was the variance. You can also write variance of g of x. Yeah, and this will be the definition in case of discrete. This will be the definition in case of continuous. That is something we can do very easily. And yeah, if you want to prove it, you can even prove it. Again, this proof will require a quick proof for both of them will require to use the fact that E is linear. If you just remember that, you can prove any of these things. You just expand it and things like that. What I would also like you to do is this. Now that we know this definition, what will be a computational version of it, which is easy to compute? Can you suggest that as well? So let's continue. What was the computational version here? Easy to compute. E x squared minus
Mu
mu
squared.
squared. So we can do the same here. It will be E g of x squared, right? And here you need a bracket to make sure that the squaring is done before the E, right? And this will be mu squared. So that is obvious. So you can try this. We can now try this box with this example. Example 4.11. So in example 4.11, we are given a distribution. So we are given a random variable. And whenever you speak of a random variable, you must have a distribution. So distribution is given. And then we are given a function, g of x, which in this case is 2x plus 1. So we need to use this distribution to figure out the variance of this random variable, which is not x but 2x plus 3. So if we start with this, how do we do? It will be variance of 2x plus 3, right? And if you want, you can also do it like this: sigma squared 2x plus 3. It's up to you. And this will be expectation of
2x plus 3.
no, but what do you want to write? You want to write the um, you want to write this thing, yeah? So first you have to write the square, right? And then 2x plus 3. This will be your g of x, right? I'm just writing g of x here. Minus, then I need to write this. So it will be mu 2x plus 3. And then square, and then, yeah, then the expectation. And you know how to work each one of it. You know how to work mean of 2x plus 3. Mean of 2x plus 3, if you think about it, it is actually expectation of 2x plus 3, right? And for that, you already know the formula. That is the, because it is, in this case, it is a density. Yeah, it is, sorry, it is a discrete random variable, so you know how to compute that. It would be sigma 2x plus 3. Now I'm writing small x, yeah? And then this f of x. And then x from 0 to 3. So that you can do. So if you now follow up the example, you will see that he will be computing this, just like I suggested. And after that, he has to compute this thing. And for that, this will be your new function. So let's follow it up. Let's, as I suggested, he starts with e of 2x plus 3, right? E of 2x plus 3. And you can alternatively write it in this way. Yeah. So it's up to you whether you use this notation or whether you use this notation. And the rest is simply that summation, right? So you're done with this. And then once you have this quantity, then you can get to this formula and the variance. And you're just plugging this. There's no fancy thing going on. Yeah. And yeah, because you know the number now, this number is 6. So you just replace this with 6. And once you replace this with 6, let's simplify this, okay? So if I now start with this, it will be e, I know it will be square, so g of x is 2x plus 3. And now you have that minus mu, and that minus mu is 6. So you can now simplify this. 2x plus 3 minus 6 is 2x minus 6. Yeah. And then square, and then t. So you can now use the same formula, but this time it will be sigma summation, and you will again have this f of x, because every expectation will have this f of x, that's for sure. Now the thing is, what do you write here? In this case, it will be 2x minus 6. So I'll just write 2x minus 6, and because it is a square, so square, and all possible values of x, which is 0 to 3. So you should expect this formula in the follow-up. You see, that's what is done here. So you simplify, and once you simplify it, yeah, okay. So here it's good that yeah, this is one way of doing it. Okay, you can actually skip this, because I would always like you to go for the basic version first. So you can compute this square right from, so it's in a way 2x minus 3 squared, right? You can have this as a separate row because that always gives you confidence. Okay, so I'm now removing everything just to make sure that you follow. So imagine you want to use the basic formula given to you in the box. So you want this basic formula. Okay, this one. So far we have, what was this? So far we have managed to find the mean of this. So the mean of g of x is 3. And we also managed this quantity, which is 2x minus 3 after we incorporated that. No, squared, sorry, squared. So let's have a second row, a third row for 2x minus 3 whole squared. And this time I'll replace capital X with small x. So you can now compute each one of them. So just to make sure you know what you are doing, what should I write here in the first entry? 2 times 0, right? Minus 3, which is minus 3, and minus 3 squared is 9. What do I do here? That is 2 times 1, which is 2. 2 minus 3 is minus 1. Minus 1 squared is 1. And 2 times 2 is 4. 4 minus 3 is 1 again, so it will be 1 again. And 2 times 3 is 6. 6 minus 3 is 3. 3 squared is 9, right? So 9, 1, 1, 9. What do we do next? All we need to do is you can think of it as your new g of x. Yeah? This is your new g of x. And the expected value will be, you can now get rid of this this thing. So forget about x now. Now you have to play with these two rows, this one and this one, because in expectation, you multiply the density or the PMF with the concerned values. So now what we do, we need to multiply these two. So 1/4 times 9, right? Plus 1/8 times 1 plus half times 1 plus 1/8 times 9, and this should give you your variance. Variance of what? Write it down. 2x plus 3. So the reason I did it this way, because I want you to remember how to apply this formula in the most basic form. Now what he has done in the example, he has applied the trick where you apply the linearity, yeah, you expand it, and then you have that simple formula. So this is what you do here. After this, he's applying the squaring operation. So you square it, and after you square it, okay, I thought he's using some computational rule, but he's not using it. He's using this. So I don't think there's no point in expanding this. This will only be justified if you want a simpler formula. So I don't think you gain anything by doing that. Okay. So we now have a practice example for this version of the formula. Another one we need is for this version of the formula, right? When you have a continuous random variable. So I think, yeah, we don't have one here. So maybe we can go back to some other, let's go back to example 4.10 and make one example ourselves out of this. So imagine you are given a random variable x continuous, yeah, which in this example is the weekly demand for a drinking water product in thousands of liters. We see, that's what I told you. Whenever you go from the physical world to mathematical world, you have to specify the units so that you don't have to write, yeah, this every time. from a local chain of efficiency stores in a continuous random variable having. So the probability distribution is given to you. And here he is asking for the mean and variance effects, which we already did. But this time, let's say we use the same function, this function, 2x plus 3 there. So let's say in this example, we are not interested in the mean and variance of x, but we are interested in the mean and variance of 2x plus 3. That is our g of x, right? So what do we do here? We need to make sure that we use this formula, right? This one. So what do we need first? We first need mu g of x, right? So what is mu g of x? Mu, it will be mu 2x plus 3, which is expected value of 2x plus 3, right? And it will be the integral density, right? And this will be 2x plus 3, 2x plus 3. This density is 0 everywhere except this region 1 to 2, so the limits will be essentially from 1 to 2. And f of x I can replace with 2x minus 1, and the rest you can do yourself. So now once you have this, the next thing is to start with the formula of the variance for 2x plus 3, and that will be expected value of right square, and then here goes to g of x, which is 2x plus 3 minus the mean of this. Yeah. So if you work this out, you will have an expression. It will not be an expression, it will be a number basically. It will be a number, and that number will come here, and then you can simplify this and then take the square and then carry on with this computation yourself. Okay. So that was it for the variance. So we have now completed this part, which I just started. Yeah. So we know how to deal with the expectation of a random variable, then the expectation of a related random variable, g of x. And then we have the variance of x, and then the variance of a related random variable. So yeah, you should always also think of it as a measurement process. Yeah, although you have not taken a course in measurements, but this way of going from the distribution of x to, so although you don't know the distribution of g, but you still manage to compute the mean and the variance and any other quantity of interest without knowing the distribution of g. You are using the distribution of x to compute quantities for some other random variable. This is a very good thing to have. So you can think of it as a measurement process. Let's say you have a measurement unit which can only measure. So let's say there's the actual, let's say you can only measure voltage. So this is the voltage, the actual voltage, and this is the measured voltage, measured voltage. And if you have some formula, you can then compute the power, right? So you don't need to measure the power, you can compute the power from the measured voltage. That's the analogy here. So because you know the distribution of x, you know everything about x, all the uncertainty related to x, and then you want to compute these expected values for g of x, but you want to do it without knowing the distribution of g of x. That is a difficult task. So these formulas help there. Yeah. So just like you can save a power meter, right? By just using the formula, here you can save the effort of building a new distribution just by using these formulas. This is a big thing to have. Now, the next thing which we need to start is this. So far, we have been dealing with only one variable, right? So, if you have two variables, x and y, for two variables, of course, you can have a distribution, joint distribution, fxy. Here, you can just write xy, or you can even write x comma y. It's up to you. So, and then um, of x, y, the specific values, and this will be your distribution, the joint distribution uh, for both x and y. Now we know how to work ex. We also know how to work ey, and we can also work how to work. We can also compute e of some function of gx, x and y. So instead of working with x and y, we can say, okay, let's say we have a function g of x and y, and then we want to compute this, so on and so forth. But and then we also learned variance. So variance of x, variance of y, and variance of some function of x and y. But these variances don't tell us how x and y. So if I ask you about this, if I ask you about this thing only, this thing, this tells you if I have a plot of f x of x. Now I'm looking for the marginal distribution, right? And let's say the distribution is something like that. Okay, so what you can say that, okay, the variance roughly tells me how wide the distribution is, right? And that is everywhere else. And I can have a similar imagination about the distribution, the marginal distribution of y. Yeah, it can have some other distribution. Now, what is the disadvantage in this picture? Because you can only talk about marginal distributions, right? Marginal distributions. We need a quantity which says something like this. Yeah, so we are looking for a some expectation which will not be variance, which will not be mean, but it will be something, or I will say some measure, a measure. We need a measure of spread for the joint distribution, right? Joint distribution. So imagine a two-dimensional distribution. Let's say this is x, this is y, and this is f of xy, and we have some surface, right? And we want to know how wide is that surface, right? And none of these two can help us there, right? Because they only work in one dimension. So imagine we need some, let's use the same symbol, sigma square. But instead of writing x here, um, let's write x, y here. I'm not sure if he's writing square there. I just want to know because this is a new thing. No, it's not this one. We need to be consistent with the, yeah. So okay. So he's not using the square there. Yeah, he's not using any square there. But instead of writing x, so if I simply say sigma x, this will be the standard deviation of x. And if I write x comma y or xy, I mean, whether you write a square or not is based on convention. Okay. So this will be something related to, it is, it will represent what we are searching for. Yeah? It will be a measure of spread for the joint distribution. So now to construct this, it has to be some expectation, of course. But how to construct that? Now let me give you some insight of what to expect. So let's say the reason you would be looking for this joint distribution is that let's say you have a process. You can think of a process or a system like you have in signal and systems where the input is, let's say, one random variable, and there is a related random variable y, right, which is related to x through some process or through some system, and you want to see how if, and for a moment let's forget about the uncertainty. Let's say there is no uncertainty, because that makes our thinking process easier. So if they were just normal variables, not random variables, so you would expect a relationship between them. So let's say this is one quantity is listed on one axis, the other quantity is listed on the other axis, and you can imagine some relationship. What will be the simplest relationship between these two? Can you imagine? What kind of relationship between x and y if there was no randomness? You would expect some straight line, right? Something like that, of any slope. All right. So we are looking, these are called linear relationships. You already know it from signals and systems, linear relationships. Now bring the uncertainty to this problem. So of course you won't have this graph, but you can imagine, now I can imagine y, x, and I can ask whether y, in general, y will be some function of x, of course, but I'm now investigating, because I don't know this g of x, I'm investigating to what extent is this g of x a linear function, some function which is like a times x plus b, right? This a and b will be unknown. So I'm now putting the question mark. I'm just asking, if I claim that this unknown g of x is linear, whether I know a and b or not, that's a separate thing. But how good is this claim? Yeah. Or in other words, to what extent, I'm asking this question, to what extent is the relationship between x and y linear? I'm just looking for a linear relationship. And if there is one, how good that will be an approximation, right? So, so that means that the expectation, if I'm looking for this sigma xy, this will be the expectation of simply, and we also want, uh, we're not just looking for x for the relationship. We also want how the deviations, because after all we want a generalization of the variance. So the variance looks for x minus mu squared, right? So instead of, you can think of it as x minus mu times x minus mu. So you are multiplying x minus mu with itself, yeah, deviation, and then the deviation of x alone. What if we now replace the second one with the deviation of y? So this will be the product of their deviation. So if I now say x minus mu times y minus mu. Now this is mu for x and this is mu for y, right? Mu x, mu y. And this will be a kind of joint variance. You can think of it as joint variance. It's not variance of x, it's not variance of y, but you can think of it as a covariance.
Covariance. Yeah.
Sorry, covariance, right? Covariance is a better word. And that's exactly what it's called. Okay, the name is misleading, okay? If you look at the name, you will, so it does not have the same status as joint distribution, because joint distribution is a complete picture, okay? It tells you the distribution of x and y in actually in full details. But this is not a covariance in full details. You are just looking for linear relationships. Now, what I mean by this is following. So if you think about, imagine a table with these values, right? So if I have a table where here I look for values of x minus mu squared, I just list those values here. And here I list y minus, sorry, mu x and y minus mu x squared. And I now replace this with small x and small y. Sorry, small y minus mu y. And I list these values there. Okay. And now I multiply. I multiply these two values. I multiply these two values. These two values. Yeah. So the picture I have in mind is this linear relationship. So if two things have linear relationships, if one of them is, for example, large, if they are related, you would expect this to be large as well, right? If this is small, that's what linear relationship tells you, and the only difference will be sign. Yeah. So you can have a plus and minus if the slope is different, but they will magnitude-wise they will follow a similar pattern. So if this is smaller, this will be smaller as well in magnitude. So they will co-vary. That's why we say co. They will co-vary. One going up, the other also goes up. And if it goes down, it will only be a change of sign. Magnitude-wise, they will both increase. So if you now take that expected value, which will involve a summation or an integral, you expect a large value at the end because things don't cancel out, right? So if I now have a picture in mind, let's say I have one signal and then have another signal and I multiply these two signals because this is what we do. We just multiply these two deviations. And if I multiply these two and then I take the average, right? So the average of the product. So if these two signals are related, yeah, the large will match the large positive, the negative large will match the negative large, or so they will vary in an organized fashion, and the overall average value will be large. But if they are not related, which means they don't have any linear relationship, their relationship is either non-linear or they are not related at all. So maybe if I have a possibility diagram, so x and y, two possibilities, either they are related or unrelated, right? And in related, you are then asking two further questions. Is the relationship linear or is it non-linear? We are not looking for this. We are not looking for this. We are only looking for this. When we choose the definition of covariance in this way, we are only looking for linear relationship. So we expect this quantity to be large only when x and y are linearly related. So I think that's enough motivation for the definition now. Yeah, this is now our definition. So if you choose g of x to be x minus mu x times y minus mu y, um, where mu x is the expectation of x, mu y is the expectation of y, um, we can have a new quantity called covariance of x and y, and you can denote it either as COV of x comma y, just like VAR, and the other notation will be sigma xy, sigma xy. I have seen some books actually writing a square there, but I don't. Yeah, we can stick with this notation. More important is this x and y together, right? So now here we have these two versions for discrete. Yeah, this side will be the same, but it will be a summation and it will be an integral. And remember, this is now the explanation. I just tried it. So you expect large values of x to co-vary with large values of y, and small values of x will appear with small values of y. So that means that when x minus mu x is positive, then y minus mu y will also be positive. Yeah. And if x minus mu x is negative, y minus mu y will also be. This is what you are guessing, and then the whole product and the average value is expected to be large. Now, so we just discussed the magnitude. Yeah, large value of this thing would mean that they are related. Now, whether that large value is positive or negative will tell us whether the relationship is of this kind or the relationship is of this kind. So that's not a big deal. Sign will just tell us whether they co-vary, yeah, in this fashion, or whether they co-vary in this fashion. And a computational version of that will be just like we had it for the variance. Huh? So for the variance, if you remember, what was the computational version? It was squared, the expectation of square x minus x squared. So now you replace this with expectation of x times y, and this will be the product of two expectations, mu x times mu y. And you can prove it easily. And the proof will always require you to use the fact that E is linear. That's all you need to know.
Sir, are x and y variables that depend on each other based on the context of? Are
The
x
thing is,
and y, do they have to be variables that depend on each other? Or can it be anything?
that we cannot say that, because all we know is this. Okay, all we know is that we have two random variables, x and y. This is from where I started. Okay, and for them we know f x y, right? Now the thing is this: if you know f x and y, then you don't need this covariance. Why? This is actually at the heart of what you're trying to ask. Why would I need this when I know this? There, I know a complete picture of how x and y are distributed. That will tell me whether they are related or not, right? So,
Yeah.
so there are two lines of thought which you must have. Either you know the mathematical form and you don't want to think about it, or you can't make sense of it. It's too complicated. So you just want a simple picture. Okay, I'm not interested in the full relationship. I'm just I just need to know whether x and y are linearly related, because this is a question about a linear relationship. Yeah? This is not a question about a linear relationship. So maybe it turns out this may, if I now ask you one thing, yeah, we had it in one of the chapters. What if it turns out that f of xy is simply the product of the two? What will you conclude from this? Let's say you find it out that x and y are such that I can factor the distribution like that. What will this mean? That x and y are
Independent.
independent, right? Independent. And this can still give you something, but this will be misleading because you know they are independent, right? So this is
Yeah.
just a guessing game. This will be more useful in statistics, right? Because in statistics, we start with data. We don't have this distribution. So the first thing, let's say you get values for a quantity, and then you get values for another quantity, and of course, because you don't have the details, so you will model them as random variables. So, but when you start from statistics, you don't have that f of xy. That is not available to you. So a good starting point for you will be this. Yeah, you can, of course, the way we define expectation is we require f of xy, but you also know from chapter 1 that you can have sample variance and sample mean. So you can have sample covariance, right? You can have, and sample covariance will be computed from the data, right? You will have sample mean. This will be replaced with sample mean and sample mean. So there you can get an idea of whether they are related, linear related or not. So it's a kind of tool which you will find useful there. At the moment, you should view this as a summary. So because here we assume that we do know f of xy, so we just want to summarize. We don't want this full picture. We just want a quick summary. Just like mu x alone. What is mu x? It's just a summary, right? It's a quick. It's just one number telling you um, something about the distribution. Rather than going for the full distribution, you just look for the location. Then sigma x squared. This is again just one number telling you something about how wide the distribution is. So if I now,
Say if the covariance between two variables is very small,
yeah,
then that means their difference is very small and they're related.
no, what we can say is that they are not related linearly. Linearly, they may be related non-linearly. The
Oh,
covariance cannot tell you anything about non-linear relationship. That's why I told you about this diagram. Right? You must have this in mind. Covariance only tells you about linear relationship. So when the covariance is very small, it means that they are not linear. But then they can be non-linear and they can be unrelated. But you will not be able to tell that. Okay. For that you will need other ways of guessing. And this is a very common mistake. People think that a small covariance mean that there is no relationship. Yeah. So you should read this and then you will. I mean, he's making it very explicit here. I'm just highlighting. Note that the covariance only describes the linear relationship between two random. Therefore, if a covariance between x and y is zero, x and y may have a non-linear relationship, which
nonlinear.
means that they are not necessarily independent. They may still be dependent. Yeah. And you will also learn something else. If x and y, this is what I didn't tell you so far. If x and y are statistically independent, let's say you know this, you know x and y are independent, right? Just like I said it on the other page where when you can factor the distribution. So what will happen, you can show it mathematically that the covariance will be zero. It will be zero. You can even prove it, right? So you just have to start with this formula, you expand it, and because you will be able to factor this, and when you carry on with the summation, it will turn out that there, and it's all good. It's intuitively also very clear. But you should not expect the other thing. The converse is, however, not true. Two variables may have zero covariance, and they will still be dependent on each other. Yeah. So if you know they are independent, then you can say. So if let me just uh, express this in the language of logic. Yeah. So if I say x, y independent, right? If I know this, this implies that the covariance of x and y is, tell me,
Zero.
zero, right? But that doesn't mean that I start from this. If the covariance of x and y is zero, I cannot conclude, I'm just borrowing that x and y are independent. Why? I already told you the reason.
Because they can be nonlinear.
It can be nonlinear. Yeah. So this is a limitation of the covariance. And this is a very simple practice example, you have two random variables and the joint distribution is given to you. These are values of x, these are values of y, yeah, and these are marginal distributions. And if you just read it, and this was also, yeah, I mean, he is repeating it. It's a previous example, 3.14. It describes a situation involving the number of blue refills x and the number of red refills y. I think we did this sometime. Two refills for a ballpoint pen are selected at random from a certain box. Yeah. I remember the distribution was something like this. It was something like 2 from 8. I don't know. And there was this x2. I can't remember the exact formula, but yeah, this thing was given, right? So now you need the covariance of x and y. So what do we need? We need to get back to the formula. So if you want to use this formula, it's very easy. You just work out the mean of x, the mean of y, and then the mean of x times y, or the expectation of x times y. Three things, right? So from this, first we need the mean of x, and for the mean of x, we'll use this distribution, right? So from this distribution, we will work out the mean of x, then the mean of y. For that, we will use this distribution, right? And try to replace this h of y with f y of y, and replace this g of x with f x of x, to be very clear. So yeah, he has now computed mu x, and you can see that in this computation, this distribution was used, yeah, 5/14, 15/28, 3/28, and value 0, 1, 2, 0, 1, 2, right? And same is the case with mu y, this distribution, 15/28, 3/7, 1/28, and 0, 1, 2, 0, 1, 2. So you are done with mu, and the next thing now is you need expectation of x times y. You can also write this as mu. What should I write in the subscript?
XY.
Yeah, you can do that as well. And this should be enough to convince you that writing fxy is not a good idea in the subscript. You should write x comma y. Can you guess why? Why do I need that comma? Compare it with this. Yeah, this is x times y, right? So anyone who is easy to be confused, he can think of it as x times y. We know it's not x times y, so it's x comma y. So this, now how do we compute this? We will compute this from this table, but not using the marginal distribution, but the full distribution, right? This one. So it will simply be 0 times 0. So you know the formula will be like this: x times y, f of x comma y, all values of x comma y, double sum. So yeah, 0 times 0 times 3/28, 0 times 1 times 9/28, 2 times 2 times. You see, you know how to compute that, right? Okay. So so now I see why he has not shown that computation of this one. He's picking it from 4.6. So he is they have done the computation in 4.6, and from that example, you know that expectation of x times y is 3/4. This probably this is the example which we did yesterday. So then you just need to plug everything into this formula, right? This will be, what was it? 3/14. So this will be 3/14 minus mu x times mu y. What is mu x? 3/4. And what is mu y? 1/2. 1/2. And you compute it. I don't know if I told you this. I haven't told you this in the class because I'm teaching signal and systems to computer engineering. So how do you distinguish between this 2.3 and when I want to say that multiply 2 times 3? So how do I distinguish between these two? Do you know that?
The decimal point is like on the base, I guess.
No, say it again. The
The
decimal.
placement is different. For the decimal point, it's like a little bit below.
Yeah, that's the important. They look the same in size, but the decimal point has to be at the base, right? They will have to be in this line, right? And this is a center. That's why it's called a center dot. This is a center dot. Yeah, and so that was a practice example for discrete random variables, and you can have a similar situation for continuous. Yeah, if you have two continuous random variables, the joint distribution is given, and of course you need marginal densities. Yeah, so it will be fx of x, and this will be fy of y. The reason you need marginal distributions is that you will need this for computing mu x, which you do there, mu x, and this will be needed to compute mu y, right? Mu y. Okay, he has done it in this one line. Mu y, mu x. Yeah, mu y requires this marginal distribution. Mu x requires that marginal distribution. And the next thing is to compute expected value of x times y. And x times y is a simple computation. You would simply say, okay, xy is in double integral x times y and this f of xy. This f of xy we know is 8 times x times y, and the limits are, and it is 0 elsewhere, dx dy, right? So it will be, the limit of x will be, x is bit, I mean, it is very misleading to say that x will be, because the inner limits are x, between 0 and 1, but they're not between 0 and 1, they're between y and 1, right? If you think about x alone, it is between y and 1. And what are the limits of y? Between 0 and
And x.
0 and x. It will be between 0 and 1. Why?
Oh, because y and x are equal
Yeah,
in that limit.
yeah, yeah. You have to go with the upper limit, right? And the best thing to avoid this confusion is to draw the region in xy plane. It's very easy. So now draw it. Y is between 0 and x. X is between 0 and 1, and y between. So how do I draw this region? First, draw the line y equals x side. This should be y equals x. And then y is from 0 to x to x. So it is this region, right? And then x is from
0 to 1.
1. So it will be this region, right? Yeah, so x is between 0 and 1. And y is between 0 and x. Yeah, so it should be this. We should have it like this, dy dx, and it will be, if you want to use this region, right, it will be um, y is between 0 and x is between 0 and 1. This is one way of doing it, okay? What would be another way of doing it? That's not the only way, right? You can now think of it in this way. So this is, you can go in this direction, right? So this will be a lower limit for x. Lower limit for x will be x is equal to y, right? So it will be y to higher limit of is 1. Yeah, y to 1 for x, and then y is from 0 to 1, right? So both, they are both correct. I mean, you must have learned this in multivariable calculus. You can either go
Yeah.
in this direction or in this direction. Okay, so now we get to that point. What did I tell you uh, about? So now we know three things, right? Just to recap, we know three things. We know uh, EX, EY separately as locations. Yeah. So locations, measures of location for the distributions of X and Y individually. So this will be mu X and mu Y. Then we have some measure of the spread of each one of them, which will be sigma X. And normally when you look at the width, you don't write this way, you just say standard deviation. And standard deviation, sigma Y. Because if you square it, then it will be the square of the width. And we also know, now we also know X comma Y, which is the covariance. But to compare these two, or to discuss the values of sigma xy, because the value of sigma xy will depend. Let's now decompose this, right? So xy is x minus mu, y minus mu, and this will be xy minus mu x mu y. Now remember the units of x and y, uh, by the units I mean the units from which they have been converted, and the units of mu x and mu y, they will influence this. So large values. So if you want two cases, let's say I have x y here, and I have other variables w z here, and I know the covariance of x y, and I know the covariance of w z. It will not be fair to compare these two covariances, because x y may have one sets of units, w z may have other sets of units. So the units, and even if they have the same units, maybe the scales are different. Maybe x and y vary between 0 and 10, and maybe w varies between minus 10, minus 100, and plus 100, right? So there are two problems which makes this comparison difficult. One is units; they may be different, and one is called the scale. Even the same units cannot help you. Uh, the example I typically give you is that even if you have two persons, they have the same account in rupees. One person's account is in 100 rupees, and the other one is in billion rupees. Now, the fact that they have the same currency doesn't help. Yeah. So scale and unit, they are both problematic. We need definitions that do not depend on units and they do not depend on scale. So what do we do? Right. This is a new definition which is called the correlation coefficient, right? And the thing I just told you is this sigma xy is not scale free, it depends on the scale. And it will also depends on the units, right? So you need a scale free version of covariance, and that is called correlation coefficient. What it does is this: it divides the covariance by both the standard deviation. It first divides it by the standard deviation of x, and then it divides it by the standard deviation of y. Why does this get rid of the scale? It's very easy. If you have a distribution of x, right, f of x, so sigma x tells you how wide that distribution is. Yeah. So if the scale, it carries the scale. Yeah. If it varies between minus 100 and 100, this will be roughly 200. If it varies between minus 1000 and 1000, this will be 2000. And it also carries the units in some way. And same will be the case for the marginal distribution of y. So if you divide this by both sigma x and sigma y, then the units will cancel out and the scales will cancel out as well. So this quantity will always be between minus 1 and 1, right? And you can prove it using calculus. So it cannot be, and this one will be the extreme when they are linearly related, right? And this way, this minus 1. So if I now draw this in a diagram, imagine two variables x and y. So this will be one extreme, that they are literally equal. This will be, let me use another color. This will be the other extreme, and this will be something in between. So all the coefficients, so this correlation coefficient, which is typically written as rho x comma y. Rho comma x comma y is covariance of x comma y divided by sigma x times sigma y. So this is between, sorry, this is between minus 1 and plus 1. So plus 1 is this extreme when rho is equal to 1, and rho is equal to minus 1 is this extreme, and all the other cases are in between. So this also means that when the correlation coefficient is close to minus 1, you cannot say that there is no correlation. You will simply say there is negative correlation. Yeah. So what will be no correlation here? What will be the value of rho which will give us no correlation? Hmm? So I told you plus 1 will mean highly or strongly correlated. Negative 1 will mean strongly negatively correlated. Plus 1 will be strongly positive correlated. So no correlation will be 0, right? 0. That is something we already know. Because when the numerator is 0, then the denominator cannot help. So you can even compute these coefficients. Yeah. You have two random variables. This is from example 4.13, the previous example, this one. So you know all these quantities, mu x, mu y, and the covariance, minus 9 divided by 56. Now this minus 9 divided by 56 is misleading because it doesn't, uh, it includes the scale. So if you now divide this by um, yeah, first you compute the expected value of the square, then the expected value of the square of x, and from this, from these two, which formula has he used to compute the variance of x. Remember, it is expected value of x squared minus, can you tell me? Mu x squared, right? Mu x is 3/4 from that example. And here it is expected value of y squared minus mu y squared. So now you have sigma xy from that example, which is minus 9 over 56, minus 9 over 56. And now you have computed these variances. This is the variance, 45 divided by 112 is the variance. So if I take the square root, I will get the standard deviation. The variance of y is 9 over 28. So if I take the square root, I'll get the standard deviation of y. And now I need to divide this thing by the product of these two. So rho xy will be this minus 956 divided by these two. Yeah, 45, 112, 9 over 28, 112. And that will give us the value. So now this value is useful, which is minus 1 over 5 square rooted. I can now compare this with any other example. I can say, okay, these two variables are more correlated than that pair of random variables. So correlation coefficient is the answer to all the problems of units and scales. And that is the reason why you must have heard correlation more in the news than the covariance, because people use correlation when they report some relationship. Yeah, that's it from this chapter, right? We have time for questions, 5 minutes. Yeah, I would like you to think about this particular question 4.48, right? This is actually in line with with how I motivated this topic. If you have a random variable of this type, so you are now proposing that y is related to x in a linear fashion. This is a linear relationship, right? So think about it. If b is negative, right? Although it really requires you to prove it, but you can say it without proving it. If b is negative, you know this will be a relationship of this kind, right? Because b is the slope. Of course, a can be non-zero, and then a relationship will be of this kind, right? So the correlation coefficient will be -1. That's what I told you, right? But if b is positive, then the relationship will be of this kind, and then so you can now also um, use this for future discussions, that whenever rho is equal to 1, this is a pure dependence, yeah, linear dependence. And if it is -1, then it is also a linear dependence, but with a negative slope. Yeah, there are many interesting examples. And yeah, this 4.3 will start next time. Write P in the chat window, right?